Hello, class. Welcome back. This is lecture 2 for MO 869, Introduction to Autonomous Vehicles. So last time we get you introduced to autonomous vehicle technologies, mostly motivation part. Now we are going to actually talk about the autonomous vehicle technologies. The outline goes as follows. I'm going to give you a quick introduction to AV tech history, and then different types, levels of autonomous vehicles are defined by different organizations. And then we're going to talk about how ADAS, Advanced Driver Assistance System, differs from autonomous vehicles. There are different terminologies people use. They use them sometimes interchangeably, but we need to make sure we use the right term. And sometimes they mean very differently. And I'm going to go over some of the key components for autonomous driving: actuators, sensors, computer, AI, software. And then I'm going to talk about, introduce you to platforms. There are different types of platforms. There's software platform, hardware platform, vehicle platform, mobility service platform. And then I'm going to conclude lecture 2 with a couple of discussions. I'm going to leave this for the discussion session. Okay. Please take a look at these slides, and please ask questions if you have any. All right. Get started. So quick history. It all started from this challenge called 2004 DARPA Grand Challenge. DARPA stands for, I believe, Defense Agency for Research. No, I think not exactly sure. I'll have to look it up, but Defense, I think, Advanced Research Projects Agency. Anyway, it's very similar to ADD for Korea. And they created this grand challenge for autonomous vehicle, autonomous driving technology. The first one was in 2004, and Stanley won the prize. In 2005, they proposed this second grand challenge, and Carnegie Mellon Boss won the prize. And then they slightly modified the challenge. Initially, for these two grand challenges, it was mostly for outdoor field type of driving task, meaning that it was less of obstacles, less structured environments, but they made this challenge a bit more challenging, so that now they call it, they decided propose new challenge called urban urban challenge. That was in 2007. And that time, Stanford Junior won the challenge. And then the famous Google self-driving car project started in 2010, based on the technology developed over these years. Three challenges. So many of the engineers and researchers were recruited by this Google project, and they moved on to realize this self-driving car technologies. And then after a while, startups joined this game of autonomous driving tech. There's Cruise, Aptiv, Zoox, Uber, Aurora. There are many. And then OEMs also join the game of developing autonomous driving. And then they showcases their technology at CES. One of the old key contributors in challenges are these two persons, Sebastian Thrun and Chris Urmson. Sebastian Thrun was a lead researcher for Stanley, and then Chris Urmson was the lead researcher for Boss, Carnegie Mellon. And then they joined Google, the Google projects. And after a while, I don't exactly remember the number of years, but after a while, Chris Urmson leaves Google and then founded a startup called Aurora. And Hyundai Motor invested in Aurora. And then Uber also, after some time, Aurora acquires Uber's automated driving units. Uber was also working on autonomous driving tech, but then after a while, Uber decided to quit and sell the automated driving unit to Aurora. Let's take a look at Sebastian Thrun's career. He was initially at Stanford, and then won the challenge, and then he moves on to Google. And worked with the team, Christian Urmson. But then after some time, he left Google. And he also was involved with this online education system called Udacity. And he was also academically strong person, researcher. He actually published a book on probabilistic robotics. So here you can see the co-authors are Wolfram Burger, who's pretty famous in this field. his faculty in University of Freiburg in Germany. And then there's this startup called Aptiv. They they were doing quite well. They actually Hyundai Motors also invested into Aptiv, $2 billion for 50%. And if we look at history of Aptiv, it started from the autonomy. It's a spin-off, MIT spin-off, and then they also have campus in Singapore. So they had research center in Boston and Singapore. And then they switched the name of the company to Aptiv, and then they continued to attract fundings. And then after Hyundai's investment, they switched name to Motional. Now it's Motional. And then there's Cruise. It's another startup. Later on, it's acquired by General Motors. They did a pretty good job of developing autonomous driving technologies. And another startup is Zoox. They also focused on full self-driving cars. So many of these startups I introduced focused on level 5. I'll talk about these levels, but full self-driving car technologies. So hoping that driver is not necessary, so that they can realize robot taxi and stuff like that. Anyway, Zoox eventually is acquired by Amazon. Amazon is interested in obviously both transportation as well as logistics. They are selling goods online, so logistics and delivery services are very important for them. So I have these videos linked to YouTube link. So please download this PowerPoint file, and please take a look at these videos on your own. They are quite interesting videos to watch. All right. Before we talk about technical details, we need to set up this understand autonomous vehicle levels. So so different organizations propose different levels of autonomous vehicles, but this is most widely used chart for different levels of autonomous vehicles. So it starts from level 0 to level 5. Level 1 is, you can think of it as ACC, adaptive cruise control. and very simple driver assistance systems, either longitudinal or traverse guide. So there's also steering assist that also falls into this category. As soon as you go into level 2, you can take your hands off and foot off, so it can do very limited automated driving, but you still need to pay attention to the forward scene, and if anything, if accident happens, then it's the obligation, the legal liability is on the driver. And then if you move to level 3, you don't have to always look at the scene, the outside. So it says eyes off, but you still need to be awake and alert and ready to take off if vehicle asks for a takeover. If the vehicle cannot handle some upcoming scene, then vehicle will ask for takeover, and you need to be able to take over right away. And if you do not take over, then the vehicle will fall back. It'll slow down and probably make a full stop because it cannot handle the scene for some reason. And then level 4, the vehicle can handle all scenes, all scenarios within a given operation domain. This is a very important part. It's fully autonomous, so you don't have to get involved at all, but within a design domain. It's called ODD, Operation Design Domain. What that means is this is fully autonomous within a limited design domain. For instance, we can, manufacturer can design level 4 autonomous vehicles for highway driving, and they can still claim that this is level 4 because it can handle all the case scenarios, scenes that can be encountered by the vehicle on a highway scenarios. Or it can also we can also design level 4 for traffic jam scenarios. So during low speed traffic jam scenarios, the system will handle all scenes scenarios. So level 4 does not necessarily give you advanced autonomous driving feature compared to level 3. So it's all about this operation design domain, how they define it. But anyway, it won't. But within this ODD, it won't ask for a takeover. Okay, the system will handle. And then finally, level 5, you don't need a driver at all. This is really challenging because it needs to handle all scenarios, very risky, very complex, complicated scenes, and all kinds of uncertainties that are on the road, and must be able to travel from any point A to point B, any destination, any origin destination combination. So for robotaxi to be realized, we need level 5 technology, but it's taking a very long time, and people see that we still need long time to achieve fully autonomous driving. So now more practical goal is now level 3, level 4 type of autonomous driving technology, and this is, more or less driver assistance systems. And I'm going to call this either semi-autonomous driving or a type of ADAS, advanced driver assistance systems. And this is another way of looking at these levels. It gives you a little more details in how to differentiate different levels. So I verbally explained in previous slide, but if you take a look at this, it's a bit clear. So this line will give you a clear reference guideline how to differentiate different levels. So like I said, level 2 can automate the steering and acceleration by the system, and then in order for you to achieve level 3, the monitoring of driving environment also needs to be done by the vehicle so that it can request takeover or fallback on its own. But here, so here's the fallback. So fallback needs to be done by the vehicle. Okay. So in order for achieve level 4, the system needs to be able to do the fallback. But fallback can mean a lot of things, but sometimes very simple fallback is realized and applied, such as slowing down and stopping the vehicle, or ideally pulling the vehicle over to the shoulder of the road so that you don't stop in the middle of a road. So that's the type of fallback we are talking. And then if that can be done by the vehicle system, then it's called level 4 AV. But remember, up to here, there's always this term called ODD, Operation Design Domain. So you don't have to, so even these vehicle handling part doesn't necessarily have to be perfect for all domains, all scene, all scenarios. manufacturers or designers can actually define their ODD design domain. So, and these automations or system handling parts is good within the design domain. But as you move to level 5, then this ODD concept is now gone. So the vehicle needs to be able to handle all scene, all scenarios, design domains. So driver would not be necessary. Okay. And so before we move on, let's compare how ADAS technology compares with autonomous vehicle technologies. I mentioned about these two terminologies, but autonomous vehicle can be a subset of ADAS in some sense, assuming that semi-autonomous driving technology is developing. And let me make these clear. Sometimes people use this interchangeably. Sometimes people think that, especially public people, believe that autonomous vehicle technology is much superior, a higher challenging technology than ADAS, but not necessarily. And the correct way of looking at these two is sort of like this. So I would differentiate these two into this. So I think ADAS would be up to level 3 or even level 4. And ADAS, these OEMs, they are interested in developing autonomous vehicle technology for ADAS purposes or mass production vehicles. Whereas these IT companies, startups, they are interested in developing full autonomy, full self-driving cars, because they believe in, they want to create new markets, which is sort of taxi, automated logistic systems and so forth, new transportation systems. That is going to be a huge market if autonomous driving tech can be realized, full self-driving can be realized. So they are investing into this technology and shooting for level 5. But it's taking much more time than people are expecting. So their eventual goal is level 5, but they are now at the level of level 4. So within a given space, geofenced, say city where they have a map, they can realize almost level 5 like autonomous driving tech, but it's still not perfect. So it's level 4. And ADAS, their eventual goal would be level 4. But now, OEMs are mostly producing level 2. Mercedes, Hyundai, Tesla, they're all level 2. But sometimes they say they developed level 3 because they can ask for this takeover request in scenes or scenarios for the system cannot handle, and sometimes they even claim that they developed level 4 for a very limited ODD, and then with very simple fallback system. So, but it's still very limited level 4, limited ODD, limited fallback functions. And oh, by the way, their interest is different because they have two different markets. They need to develop ADAS, semi-autonomous driving tech, and then implement this onto their mass production vehicles. Whereas these startups, IT companies are shooting for a fully autonomous driving tech, and they don't really care about how expensive this vehicle is, and if this is realized, and they can create whole new market business model and markets. So, and another thing is sometimes people think that level 4 is more challenging than level 3, but not necessarily, because for ADAS you need to use affordable, low-cost sensors and computers, whereas you can use all kinds of hardwares and sensors and so on for fully self-driving car systems. So their goal is different, their business model is different, their engineering problems are different. Okay. Anyway, this is let's move on to how OEMs see this developing automated driving system from OEM perspective. They already have the market, meaning that it's not like they are startups. They already are selling their vehicles, and they need to keep this market and sell their vehicles, currently and in the near future. So they need to come up with very practical solutions, systems that can be realized with reasonable cost. So they see this as an evolutionary approach. So as of now, they're selling this level 2 systems, AEB, steering assist, auto parking, and so forth. And in the future, they are shooting for level 3, level 4 autonomous driving tech, which is highway pilots, remote parking. And then as you move on to level 4, you can do urban city pilot, and then can do valet parking, meaning that you can just let the vehicle park itself almost completely. And then if once it moves on to level 5, the autopilot full self-driving car can do all functions for driving scenes and scenarios. All right, let's before we move on to next slide, let me pause here, move on to the next slide. Okay, so far we have covered up to here. Now let's continue from the key components. So let's start with actuators. To move the vehicle, obviously we need actuators, which include powertrain, steering system, and so forth. But back in the day, when people were initially developing autonomous vehicle for these challenges, urban challenge, grand challenge, people had to put additional actuators to control the vehicle. So this doesn't look very neat. So this is quite old images when they did not have access to vehicle CAN network. But nowadays, people either reverse engineer and have access to CAN data, or they actually use some of the actuators that is already built into the vehicle, such as ACC, adaptive cruise control, and then they can also have access to MDPS, which is basically electronic power steering system. So these actuators are not now built in this vehicle for almost all vehicles. So all you have to do is have access to these controller modules and sort of manipulate these controllers so that you have access to vehicle control. Now let's take a look at sensor side. This is, you're looking at sensor configuration. So there are mainly 4 types of sensors. The 3 are shown here. First one would be camera, second radar, and then LiDAR. But many mass production vehicles are now equipped with camera and radar, but LiDAR is not widely available as of now. LiDAR is starting to deploy onto these high-end, more expensive vehicles to achieve higher level of autonomy, level 3, level 4 types of autonomy technologies. And there's ultrasonic sensors, which we'll talk about soon. when it comes to sensor configuration, we can divide that into two types. First would be sensor configuration for full self-driving, and then sensor configuration for ADAS. So here we looked at ADAS, but if you take a closer look, many of the sensors are either camera and radar. But LiDAR is rarely used. But like I said, LiDAR is sometimes used for more expensive vehicles for the front forward direction sensor only. On the other hand, if you look at sensors for full self-driving cars, you can see, all vehicles are equipped with LiDAR as a main sensor, because LiDAR gives you high accuracy, high resolution, ranging information, which is very useful for reconstructing 3D environment. Camera does not give you that type of range distance information. Radar gives you distance information, but it provides very, very noisy and sparse point cloud. So you can't really rely on these sensors alone for level 5 full self-driving target. So I also mentioned that full self-driving, the business model, the market is quite different from mass production vehicles. So if you can actually replace the driver, assuming that full self-driving capability is there, then you can use more expensive sensors such as LiDAR. So LiDAR would be a big difference between level 5 versus other levels of autonomy. Let's take a quick look at camera. I think camera is widely used for many applications. Webcam camera, digital camera, smartphones. It's everywhere. So I think everybody is familiar with this. But the only difference for automotive application is that for automotive application, it needs to be very reliable. So if you think about it, automobiles have to go through a lot of harsh environment. For instance, automobile must be able to handle very, very cold climate weathers, and and very hot weather conditions, and it can go through off-road road, and you may have crash, some impact from outside. So the vehicle needs to be able to, so vehicle parts needs to be able to, reliable under these harsh conditions. So that makes many of these sensors, automotive sensors, differ from sensors that are used for other applications. When it comes to camera, camera only the raw data you get from camera is the image, but that doesn't tell us anything about 3D environment reconstruction, such as object detection and so forth. So requires substantial signal processing to detect driving environment, static objects, dynamic objects. There are different companies investing into this camera technology, but Mobileye is dominating the market. They have more than 80% global market. Many OEMs, automobile manufacturers, are using Mobileye solutions. Mobileye is a Israeli company. This used to be a startup back in early 2010 or early 2000-ish. I was told that they took about more than 10 years to actually produce products and make profit out of it. So they had to go through this long development process period, but now they are dominating this market. And a few years ago, 2017, Mobileye was acquired by Intel. So now Mobileye is an Intel company. So Intel, I guess, wanted to expand their business towards future mobility technologies. We also have a domestic startup called Strad Vision. This is slightly old information, 2020. They are still, working on their business, trying to catch up on Mobileye. So I was told that they are producing products for Mercedes using readily available chips. So the main difference is that Mobileye, they embed their software on their own chip. So they manufacture their chip. But Strad Vision is using readily available chip and port their software algorithms onto these automotive grade chips. And I was told this is used for a Mercedes C-Class. And next sensor would be radar. Radar uses radio signal. This is an active sensor, unlike camera. Camera senses. Camera is a passive sensor, meaning that it does not actively send out signal to sense inputs to get the sensor outputs. But radar actually emits radio wave, and an antenna gets the reflected wave from the target, and this is how radar signal processing is done. Initially, you have the analog frequency domain signal, and you need to go through FFT, fast Fourier transform, and then you can obtain this 2D range Doppler sort of image-like information. And this gives you the range, distance information, and Doppler, and then 2D range azimuth information. So this would be the distance, range, and then this direction is the azimuth. And you can see that after signal processing, you see these bright points, peaking points. And you apply filter, and you extract the point cloud out of it. So this is the point that you would get from this 2D range azimuth heat map. And then using these point cloud, this is relatively sparse point cloud, and you do clustering and tracking to output object level, position and velocity information. The main difference between radar and LiDAR is that this sparsity, and the radar gives you quite noisy signal point cloud when compared to LiDAR. LiDAR is highly accurate. It provides highly accurate point cloud, and because LiDAR uses laser scanner, so that would be the main difference. So that's how LiDAR can give you much more accurate 3D point cloud and object detection performance. So let's take a close look at LiDAR. So there are different LiDAR companies and LiDAR products out there. Velodyne, Hesai, and so forth. There are actually quite many. And the way it works is that you have this laser diode, and sends out a laser beam, and then it'll reflect from the objects, whatever that is, and then you would have this return beam, and then and then you will detect the time of flight, how long it took for this laser beam to come back to this sensor, photodiode. And because of the nature of this laser scanner type LiDAR, you need this moving part, in this case this mirror, because we want to be able to detect this 360 degrees we need something to rotate this laser direction of the laser beam. So you would need motor to rotate it, and the motor will have to continuously rotate to get 360-degree information. There are two types of LiDAR, though. The first one is what I just explained. So you send this laser out, and then you get the receiver laser, the reflected light, and you can compute how long it took to get there and come back, and which is called time of flight. And for scanning LiDAR, you need to have a motor to scan the LiDAR to obtain 360-degree information. Whereas flash LiDAR, where there's something in between actually as well. The flash LiDAR sort of works like a flash. It sends out laser light towards forward direction, like a flash, and then a sensor computes the reflected photons, and you can tell what the distance for each position of the laser reflected laser information. The main difference between these two is that flash LiDAR does not require scanning device motor, such as moving parts, but flash LiDAR tends to as of now, their range is quite limited, and the resolution is also quite limited. So it's not very practical for automotive grade LiDAR, where we need 100-meter or more range with high resolution. So people are developing other types of LiDAR, such as MEMS type of LiDAR, where they still do use a moving part, but very small micro size mirror to change the direction of the laser, and so that they can cover the scene. But those type of LiDAR obviously cannot cover 360. Usually those are designed for or a field of view of those LiDAR would be 120-degree or so, something like that. Let's take a look at this clip to get a sense of how LiDAR works. So you can see the ground, you can see the pillars, vehicles, pedestrians. Now they have even higher resolution LiDARs. In that case, you can have even better, more dense and more accurate information. But LiDAR, but because it gives you very accurate information, but that also can mean this is a sensitive device, and sometimes it's quite prone to failure, malfunctions, or misalignment, and can, you know, can break or you know, malfunction quite easy. And this is quite critical when it comes to autonomous driving, because safety is critical. So and like I said, automobiles must be able to go through very harsh environments, cold, hot, rough terrain type of environments. And when it comes to weather performance, LiDAR is not perfect. So as you can see, when there's a rain, you have these noisy signals, and you must filter those out. It's not impossible, but you still need that type of filtering mechanism, algorithm, to properly use it. So there are many startups. Velodyne is probably the early age LiDAR company. Now there are Oster, Hesai, Luminar, Innoviz, Ava. Recently, I hear that Hesai Luminar is doing quite good when it comes to automotive LiDAR. So in summary, this gives you quick comparison of those three sensors. So let's take a look. Camera gives you good lateral information, but it's not very good at giving you the longitudinal information, so distance, range information. Range is, you know, it's okay because it depends on what type of lens you use. So if you use large FOV lens, then you get, you know, relatively short range. If you want a long range camera, then you would need a lens for that, and your FOV, field of view, will decrease. as you increase the range. The cost is quite affordable. Classification is super great. It's probably the best among all sensors because it gives you this rich color information, image information, and dense as well. Weather sensitivity is not so great. So when it's raining, the view can easily deteriorate, and you will either need to physically wipe out the water droplets to keep it clean. But maintenance durability is great. If you look at radar, radar gives you good distance range information, but lateral is not so great. It's quite noisy, and assuming that you're using array type of antenna, which is the case for automotive grade radars. Range cost is great, but because of the sparse and noisy point cloud information, classification is not so strong factor for radar weather-wise, but it's a very robust, very good, meaning that even if it rains, radar can give you consistent and reliable point cloud. Also, maintenance durability is great. No moving parts for camera and radar. But let's move on to LiDAR. LiDAR is the best sensor when it comes to accuracy, distance and lateral information, because you are using this laser light, but range it depends. So if you're using low channel LiDAR, then the range substantially decreases. So you get only about 50 meters or so when it comes to detection performance. If you do not have high resolution LiDAR. But if you use high resolution long range LiDAR, then you can get longer range. But still, it's not great because it depends on the resolution. Cost obviously is not the strongest aspect of LiDAR. It's quite expensive. Classification it's okay, I guess. If you use high resolution LiDAR, then maybe you can tell what it is, but still you can only tell it from the shape of the point cloud. So it's compared to camera, you don't have that dense, rich features you can classify. Weather sensitivity, you saw the rainy scene, so it's not that strong, but it's still usable up to some level. But I think one of the weakest point for LiDAR is the maintenance, durability, reliability. So it's quite sensitive. and if it fails, then you need to replace it, and it's expensive. So that's why LiDAR has not been widely accepted for mass production vehicles, because it's quite cost sensitive. But if you take a look at these comments, bullet points, one point I want you to keep in mind is camera and radar are complementary, meaning that radar is good for longitudinal, where camera is not so strong at, and camera is strong at giving you lateral information, where radar is not. So range-wise, they're also complementary, classification complementary, weather sensitivity complementary. So if we can properly fuse these two sensors, then hopefully we can get a very robust, very reliable perception outputs. And there's also one keyword when it comes to perception. It's redundancy. So for autonomous driving, the safety is critical to obtain higher level of safety. People agree that we need redundancy. Redundancy in sensors, redundancy in actuators, so that if something fails, then the other sensor, the other actuator can at least put the car into the shoulder, or do some sort of fallback operations, rather than just dropping the autonomous mode and do nothing, and that can really critical when it comes to safety. So redundancy is important. Okay. And then there's ultrasonic sensor. Ultrasonic sensor uses ultrasound, so people cannot hear, but it emits this ultrasound, and then receives, senses this echo sound, and then you can tell the distance to the object. So this works similar to radar, in a sense that it's active, and it's not very good at azimuth information, lateral information. So you can tell there is an object and how far it is, but ultrasonic sensor cannot exactly tell where the object is in the lateral direction or angular position. So that's why you have multiple ultrasonic sensors around the bumper, front and rear bumper. And also ultrasonic sensors can only give you very short range. So it's suitable for parking purposes, parking application. And then there's DGPS, RTK. We know that we can find our position using satellites. We need these four satellites to compute the position of the GPS around the globe, but it may contain errors, especially when you have low cost GPS, and or when you have if you're in urban canyon or in city environment, you have a lot of obstacles, and these signals can reflect from different obstacles and can give you wrong signal, and which will give you a large position estimation error. So GPS is usually only reliable when you're in open space. Okay. But if you use high-end expensive GPS, such as DGPS, differential GPS, and if you also have access to network internet, if you're connected, then you can also correct your position based on this reference position base. That way you can really get very accurate information, and you can also fuse that with IMU. I will talk about that later. But if you use high-end DGPS RTK and fuse that with IMU, then you can get centimeter level accuracy. So this can be used for localization problem. But like I said, in urban environments, in metro city environment, even high-end DGPS doesn't work reliably. So you need other localization methods to handle localization problem in city environments where tall buildings are everywhere. That's where map-based localization comes in. Here's IMU. It stands for inertial measurement units. Inertial measurement units. So it's a relatively small device, and have this gyroscope accelerometer on the board device, so that it can output acceleration and angular rate information for robot application or vehicle application and so forth. It's a nice sensor that can directly give you acceleration and angular acceleration and angular acceleration information. But to get position information, we need to integrate this over time, and when you do that, the error tends to accumulate and drift away from the true value. So oftentimes you need to reset the true value, but still it gives you a high frequency, good incrementally reliable information. Okay. And then finally, we need a computer. We need GPU, TPU to run, AI models, where parallel computing is available. And then we have AI, deep learning technologies rapidly developing. The breakthrough in software was brought by deep learning, and I'll talk more about deep learning and AI in the following lectures, but it's combination of many things, actually, not just deep learning itself. We have computing power. We need big data. We need optimization techniques. We need network. So when we have all of these available, then we can design a network that can benefit from a large data set. So as you can see, conventional old machine learning approaches tend to give you decent performance with small number of data, using oftentimes handcrafted feature network. But then when you have large data, you can use large network, and you can use high performance computer to train the large models, so that the performance can continue to improve. And the left figure shows how deep learning actually provided a breakthrough when it comes to AI. I think where are we on switchboard? I think this was language task, but anyway, in many applications, tasks, speech group task, deep learning actually was a breakthrough, and gave superior performance compared to existing algorithms. So now some tasks are now superhuman, meaning that AI is better than human. But camera perception is actually, especially 3D perception, is still quite challenging, even for deep learning based perception models. We'll talk more about that later. Okay. So AI deep learning is now applied for many applications, many tasks, including autonomous driving. There are many tasks when it comes to perception. One task would be 3D object detection. So what that means is you need to put a bounding box for objects, so that we can reconstruct 3D environments, so we can understand where is the objects heading which direction, what size, and so forth. And then there's a software platform there are a few options. Apollo is open source software, so you can download and use it. So if you use this software, then you can relatively quickly build a autonomous vehicle. So there is a framework for real-time, perception, planning, localization. Modules are already structured in this software platform, so you can use many of these algorithms, baseline algorithms within the software. So this is a video clip provided by Baidu. And then there's another software platform called ROS. This is not designed for autonomous vehicle, but many robot applications in general. So, so there's strength and weaknesses when you compare ROS with Apollo. So there's less flexibility when it comes to Apollo, and you have more flexibility when it comes to ROS, but ROS is less, I think, tight on real-time running, whereas Apollo uses this cyber RT to run these algorithms in real time, and it's designed for autonomous driving. So many of these sensor configuration, device interfaces and architectures are designed for autonomous vehicles. And then there's this another software called AutoWare from Japan. This is ROS based software platform. So on top of ROS, people build sort of like Apollo for autonomous driving, but when compared to Apollo, AutoWare has less documentations, and less community. Community is less active, so people, usually prefer either ROS or Apollo. And then there's a software platform called AutoSAR, or Adaptive AutoSAR. This is actually initiated from automotive industry. So, in the old days, back in the days, AutoSAR was designed for functional safety, meaning that if your algorithm or hardware fails, it needs to be reliable. So you need sometimes you need redundancy, and then they have different standard to meet these functional safety standards. But back in the day, it was only giving you this very basic rules and standards, and it was mostly up to developers or manufacturers to meet these standards and try to make it more safe in functional safety sense. But now this old AUTOSA is no longer suitable for future applications such as autonomous driving. So back in the days, it was mostly for microprocessor-based controllers. But now we have much bigger, heavier computers compared to these microprocessors. So they need to now move towards new functional safety issues when you use these high performance computer GPU chips with different types of applications running on these high performance chips. So you can think of this as operating system, but it's quite different approach when compared to the softwares you saw earlier. So this adaptive AUTOSA is focusing on this functional safety from industry perspective. And then there's hardware platforms, computing platforms, obviously is necessary to run softwares. And there's NVIDIA, obviously. They developed this NVIDIA drive with developer kits. So you can they also provide software for developer, and so that you can develop your algorithms on top of this NVIDIA drive hardware. But this is quite expensive, and it's not open source, and the software is designed for their hardware. So sometimes it's not that flexible to use. And then there's hardware computer from Tesla. This is Tesla's computer, self-driving computer. They have two main chips. They say they sometimes use it for redundancy, but I think because they have multiple cameras, I think they have 7 cameras. So they need to run these 2 chips dedicated for different camera images for perception. And I think that's what this figure is showing. Okay, and then vehicle platform. So people use platform for all kinds of purposes, but so I wanted to sort of make sure we are talking about the same thing. We can use the platform for software platform, vehicle platform, and so forth, hardware platform. So there's, a vehicle from Motional, Waymo, Baidu, Navia. There's many vehicle platforms out there. And then there's a mobility service platform, right? In many cases, people use platforms for these type of services. So in Korea, we have Kakao Mobility, Uber, SoCar, for either rental or ride hailing services, taxi services. And they are also they're very interested in autonomous driving technology, and they either develop it themselves, or sometimes they develop their own autonomous vehicle technologies, and you're looking at some of those technologies, autonomous vehicles. Okay, this concludes the introduction to autonomous vehicle technologies. So we talked about history, autonomous vehicle levels, ADAS versus autonomous vehicles, some key components, different platforms. Platform may mean different platforms, and so forth. Now, I'm going to leave this section for discussion session. But please take a look at these slides and think about it before you come. Okay. So what this is there's Tesla autonomous vehicle technology, and then there's Waymo, Google self-driving car approach or technology. They are different. I talked about this briefly earlier, but the main difference between the two is the Tesla do not use LiDAR and map. If you think about it, the Tesla is mass production vehicle, Waymo is not. So their approaches are different. Please think about this. Why Tesla wouldn't use LiDAR? Why Tesla is not using HD map, whereas Waymo are using both? So this is Waymo. Waymo definitely uses LiDAR, multiple LiDARs, and it also uses HD map. Okay. And what about map, HD map? Is HD map absolutely necessary? It depends, right? So let me wrap up here. Please review the lecture materials, and please bring questions. And if you can, let us know your questions before you come. That would really help us to prepare answer to your questions. Okay. So thank you for your attention. I'll see you on Wednesday. Okay. Bye-bye.